this, and I should be ready. We're going to go on with Charles' Law. Now, before we get started, let me prelude with the idea that, do you all know Friday is a total day off of school? Okay, no remote or anything, just total day off Friday. So next time I'm going to see you is Monday. And actually Monday, grab one of those and maybe a calculator if you want before you sit down. Good to see you. Monday is the last time we're going to do a gas law with notes. And then our unit's going to wrap up since then. So we'll do a lab, we'll do a review, and then we're looking at testing literally 2 weeks from yesterday. So as much as that sounds far away, with the STAR test coming up, like, this is happening fast. There's already 6 grades in the grade book. Today's grade is going to be the 7th. Be certain you're not letting yourself fall behind. Okay. We're going to look at Charles' Law today. I've passed out the paper to those in the classroom, online students. There is a copy for you to download if you didn't print it off the email. You're also welcome just to make notes on paper, and you can pull up the version online and look at the two together and figure out what went on as well. So Charles' Law, and I don't know how to say his name correctly because it's French, which is ironic because I'm told my last name is French. I don't speak French at all, but I'm going to call him Jacques Charles. He did experiments with gases and he found a connection between volume and temperature. So we've not looked at a volume and temperature connection yet. That's why we're looking at his law today. We are going to start off like we've done before with some graphing. So I have some data, and we're going to graph this data and see what kind of connection, direct or inverse, is between volume and temperature. And of course, I'm trying to walk away from my computer, and that's when everyone wants to be let in. Okay, we're going to, okay, I'm trying to walk away now. Don't bug me. Thank you. Okay, all right. Now we have done, let's see, we're going to put volume. No, I wanted my pen. There we go. We're going to put volume here on the left, and our volume is going to be measured in liters. That's going to leave us temperature on the bottom, and temperature is going to be in Kelvin. Last time we talked about temperatures in Kelvin. We'll review that because you need temperature in Kelvin. And we've already done the numbering before, so I don't need to recount. I know that going by 0.2s works on this side. That's a 1.6, 1.8, 2.0, 2.2, 2.4. I could go up to 2.6 and so on. Yep. So we've done that. Now I do have different numbers to put on the bottom, and I need to go from like 125 to 300. So I'm going to count by 25s and see how we fit and just see what happens here. So 125, 150, 175, 200, 225, 250, 275, 300. Yes, that works well. So we're going to go 125, 150, 175, 200, 225, 250, 275, 300. I'll go up to 325 just for fun. There we go. And now I'm going to start placing my dots. So at 1, I have 125, so that's there. And 1.2 is 150. 1.4, hey, it looks like they're all hitting the vertices, which is kind of handy for drawing those circles for my dots, big dots. Love to see them after you draw the line through them. Okay, now that's all the data we have. We're still going to draw our line through the whole graph because that's what we do. It takes an average of our data. Now this is where I would grab my ID and I would use it as a straight edge and I would shoot a straight line through all those dots. I'm going to try to freehand this. I can't imagine this is going to go well, but for you on your paper, attempt, wow, no, this is not going well. But attempt to draw a straight line through all those, and then there's our relationship. So now we ask that all important question as temperature goes up. So as I go from left to right along the bottom, what's happening to the volume? Is it going up or down? As I go from left to right across the bottom, volume's going, it's going up, isn't it? So volume's going up if temperature goes up. So they go the same way. As one goes up, the other goes up. That means they are, maybe you'll remember the word directly. They are directly related. So if one goes up as the other goes up, then if one goes down, we'd expect the other to go down. I'm going to make sure everyone's had time to fill all this in. Okay, anyone need more time? Good, okay. We're gonna do some demos and I got some real fun for you today. First one we're gonna do is just a, we're gonna start with what I'm gonna call a big balloon. So I have online students can see I have just an orange balloon blown up already here. Okay. So we're going to take this orange balloon. That's supposed to be a balloon. And these are not the droids you're looking for. Okay. I'm going to find the volume. So I have my calculator set up with the volume equation. My radius, I just threw my pad around. Oh well. My radius is 8.5 centimeters. So my volume is 2,572 milliliters. So 2,572 milliliters is my volume. And it's been sitting here at room temperature. And I have a thermometer here that's also been sitting out at room temperature, and it says 22 degrees Celsius. Now I want to pause here, because we looked last time at the fact that I can't use Celsius in gas laws. Do you remember the name of the temperature scale I have to use in gas laws? Kelvins, yeah. Okay, so we have to use the Kelvin temperature scale. So we're going to take, do you remember the magic number? 273. Now you have notes over it. You're going to be taking an open notes test. You don't need to memorize that number. But what happens when we add 273 to our Celsius? We get what kelvins? 295 kelvins. Okay, that's a K for Kelvin. I should have extended the little black box down, but there we go. So my balloon right now is rather large. It is 2,572 milliliters in volume. And I'm going to cool it down. Now, before I cool it down, I want you to predict for me what you think is going to happen as I cool it down. Should it get larger or smaller? You got a prediction? Maybe? I am attempting to adjust a window here. So there we go. Okay. So here's a little window of my demo. There's my big balloon. I'm going to cool it down. Now I'm going to step out for a moment because another teacher in the building, Miss Keith, has done us a huge favor. She has gotten us some liquid nitrogen. That's how I'm going to cool down this balloon. We're going to have some fun with that, let me tell you. So I'll be back in like 30 seconds. I'm going to go get a little cooler of liquid nitrogen. Be right back. We'll see what happens to the balloon. Cooler full of liquid nitrogen. Hopefully it lasts well for us. Drop in my balloon. Let it cook a little. Okay, actually all the online students can see is a cooler. Okay, so let's take a peek. Oh yes, it is working. Oh, this is fun. Okay, so here we go. You ready? Check it out. Doesn't it look really sickly? Oh, it's inflating again. Yeah, because it's warming up. Okay, let's try that again. Hopefully the liquid, come on. Yeah, gases can heat and cool real fast. So I'm not surprised there's a big change here. I need to be ready to measure the volume of this as soon as I pull it out. Yeah. Don't. You would like frostbite your throat. Yeah, I don't know any way that you could. If you don't die, you would not want to live through it. Okay. Okay, I am measuring real fast. Okay, I got it real fast. So we got it to go smaller. It went to, grab my calculator here. 1,150 milliliters. So it's a lot smaller. So I'm going to draw a smaller balloon. Went to 1,150 milliliters. And the temperature, liquid nitrogen's at a negative 196 degrees Celsius. Now I'm still going to add 273 to get to the kelvins. So again, kelvins will not go negative. This is still going to be a positive number going on here. So let's see what that, someone help me out there. 196 plus 273, negative 196. 77, awesome. 77 kelvins, much, much, much cooler than before. Now I'm going to attempt to do something, not sure how well this is going to work. I have seen this done. So we will see if it works again. I'm going to stick it back into the liquid nitrogen. Nope, it's just, oh, this, you'll find. It is. I may be out of liquid nitrogen to pull this off, but we're going to give it a try and see. I can, but I also need enough to last all day today and all day tomorrow. Okay, there is something in there. Okay, I'm going to attempt to show you my breath. Okay, so yeah, let's see if this actually works. Here's my balloon. It's all crinkly. Oh, come on, grab it. Thank you. My breath, yeah. Okay, see these little ice crystals coming out? That's my breath. That's the air that I blew in to inflate the balloon. That's the humidity that was in my breath. It's now these little ice crystals on the ground or on the tabletop there. So, yeah, or something. No, unfortunately, like it has pretty much all gone now. There's not much left in there. But we're going to move on to the second one. We're ready for the second one. I have a balloon attached to a bottle here. So we're going to do a bottle balloon. So I have a Coke bottle. You know, my artistic ability is limited, and I've got a balloon attached to it, and the balloon is like barely inflated. I will find you a volume though. Yeah, that's supposed to be this 2-liter Coke bottle. You know, my artistic ability is limited. But we have a volume now of 65 milliliters. So not much. And the temperature, it's at room temperature again, which we already figured out was 295 kelvins. So we can just use that. Okay, I have over here a device that's really good at making large amounts of hot water. It's meant to like cook up coffee for people. Okay, all it is water because I don't like coffee. Okay, I'm going to stick a thermometer in it to start with so that when we need the temperature, we can get that. I'm going to take my bottle with balloon and I'm going to put in the hot water. So yeah, kind of figure out what you think is going to happen. So here we go. Bottle into the hot water. Okay, so the bottle, even though we would say it's an empty bottle, there's air in the bottle. So as I heat up the bottle and the balloon, all that air is expanding. And unfortunately, it doesn't expand a whole lot. This is what I've got. But you can see it certainly is getting larger. Large enough that now we have a volume of 268 milliliters. Okay, so I have a much larger balloon on my bottle. Yeah. No, hopefully, if I'm doing this right, because I want to redo this one year after year, if I'm doing this right, it's not hot enough to actually like melt the bottle or anything. Temperature is 86 degrees Celsius. So let's fill in what we got. First off, I got my bottle. Again, my drawing is going to be bad, I know. But now the balloon's kind of inflated. My volume was 268 milliliters, and the temperature was 86 degrees Celsius. So I need help. 86 degrees Celsius plus 273. What do we end up with there? 359 Kelvin. Sounds good. So there we go. So we saw as temperature went down, the volume went down. And as temperature goes up, the volume goes up. So it's a direct relationship. If one goes up, the other goes up. If one goes down, the other goes down. And you also saw my balloon that was in the liquid nitrogen. When I pulled it out and just set it on the countertop and it warmed back up, it started reinflating, getting bigger again. Direct relationships. As one goes up, the other goes up. As one goes down, the other goes down. So that's Charles' law. Let's do some examples and then you can get to the practice in Canvas. Charles' law looks this way with a V1 on top and a T1 on bottom and a V2 on top and a T2 on bottom. I remind you volumes, milliliters or liters, both are acceptable. They would need to match in the same question, but I'm not going to do that to you. They're going to match. But that is something that is important as a chemist that we make sure before we do the calculation, they're either both milliliters or both liters. Temperature must be in kelvins, must. As you do your practice, you gotta get them into kelvins for it to work. So we're gonna be practicing that. So on the back, top left box, if 25.3 liters of fluorine gas is cooled to negative 10 degrees Celsius, where it occupies a volume of 11.8 liters at that cooler temperature, what was the original temperature in kelvins? So it is V1 over T1, V2 over T2. I do like making my little chart here of everything I'm given in the problem. So let's do that. Volume or temperature, what would be measured in liters? Volume. Let the labels tell you what it is. If you ignore the labels, you're making it harder on yourself. Okay. It is cooled to a negative 10 degrees Celsius. It becomes negative 10 degrees Celsius. That's temperature 2. Now, what do I need to do to temperature before I can do the math? I need to convert it to Kelvin. So that's why we practiced that last time. We're going to convert it to kelvins by adding 273. So it's 263 kelvins. And we're told at that new temperature, we have 11.8 liters. Temperature 1 is what I'm looking for. So I'm ready to plug in my numbers. 25.3 liters over X equals 11.8 liters over 263. You've got to use that Kelvin. It will not give you the same correct answer if you don't use kelvins. Be careful there. Okay, we're going to cross multiply divide. 25.3 times 263 kelvins, 11.8 times X. So X equals, so what do we get? 25.3 times 263 divided by 11.8. What do we end up with? Sorry, say that again. 563.9. Okay. Let's see. Now I have three, and 3 digits. So we're going to go 564. 564 kelvins. 563.98? 88. Okay, but still the 8's going to make it go up again. So we're good. Thank you. So 564 kelvins. Now notice the volume went down and my temperature, I have to draw the arrow the correct direction here, but the temperature also went down, and that's a great way to check our work. They both went down. Let's look at the top right corner. 455 milliliters of oxygen gas at 143 degrees Celsius is cooled and now occupies a volume of 321 milliliters. What's the new temperature in kelvins? Milliliters is a great way to measure I don't know why I put a P, I meant to put a V. Volume. Original temperature was 143 degrees Celsius. Oh, we can't leave it that way. We're going to have to add 273. So it looks like 614, 416 Kelvin. Someone double check that for me, please. I don't want to tell you all incorrectly. Okay, 321 milliliters. Now I can tell my volume's going down, so when I solve for my temperature, I'm hoping my temperature goes down. V1T1 equals V2T2. 455 milliliters divided by 416 kelvins, use the kelvins there, 321 milliliters, and X. So multiply 416 kelvins times 321 and divide it by 455. Yeah. All that fun we get to have next week. Yes. It's all right. So 416 times 321 divided by 455, what do we get? Okay, we're going to go, so 293 then. Thank you very much. That sounds, well, let's see if it sounds good. Volume went down. I want my temperature to go down. So from 416 to 293, was that going down? Yes, so we probably did it correctly. And since I have 3 significant digits on everything, there we go. Rounding it to 293. Any other questions so far? Okay, let's go to the lower left. An unknown amount of nitrogen gas at 13 degrees Celsius is warmed up to 33 degrees Celsius, and now it has a volume of 825. What was the original volume? Exactly. Oh, 13 degrees Celsius, can't leave it as Celsius. Let's get that to kelvins. Let's see, 286. I believe I can math. Let us hope I did that well. 8.25 liters, and new temperature is 33, no, temperature 2. 33 degrees Celsius, we're going to add 273. 306, I believe. Now look, I can tell my temperature is going up. So I hope X is smaller than 825 so it can go up. That's how I'm going to check my work. V1 over T1 equals V2 over T2. X over 286 kelvins, be sure to use the kelvins, 8.25 liters over 306 kelvins. So boom, boom, kelvins are gone. I'm going to multiply 286 times 8.25 liters and divide it by 306. If you can read my writing, that's supposed to be 306 at the bottom. I'm hoping this is less than 8.25 because I want it to have gone up. I need it smaller. So what do we get? 7.71. Oh, that's great significant digits too. Put the label liters on there. Ah, that was supposed to be a box. And then boom, there we go. 7.71 liters. I like that. Good job, everyone. So yes, volume 1 was 7 0.71, so it did go up when temperature went up. And that's a great way to check our work. Okay, bottom right box. If 325 milliliters of hydrogen at 85 degrees Celsius is warmed to 225 degrees Celsius, what will be the new volume? So volume 1, 325. Temperature 1, 85 degrees Celsius. Oopsie, got to add to it. We'll come back to that. Volume 2, I don't know. We'll find out. Temperature 2, 225 degrees Celsius. Well, got to add the 273 there as well. All right, so 273 plus 85, maybe let's see, 8 and 5 and 3. I hope I did that right. Tell me if I didn't. And then 8 and 9 and 4. And let me know if I did not do that correctly. Oh, thank you. What happened to my temperature? It went, please tell me up. Yeah, it went up. Okay, so my volume should also end up going up. Yeah, temperature went up, volume should go up. I'm not trying to trick you. That's how it works here. So there we go. Let's see what happens here. 325 milliliters over, use the kelvins, 358 kelvins equals X over 498 kelvins. So 325 milliliters times 498 kelvins divided by 358. Okay, kelvins, because kelvins are going to cancel. I meant to leave them off, but there we go. 325 times 498 divided by 358, and I'm hoping it's larger than 325. What do we get? 452 is good significant digits, and is it larger? Yes, it is. Don't forget the label, milliliters, but wow, I cannot draw a box today to save my life. Yeah, that's really sad. But there we go. You get the idea. I was trying to box the 452 there. All right. So as you work these, great way to check your work is to just ask yourself, hey, what happened to volume and what happened to temperature? And they should be the same. They should both go up or they should both go down. The work today, you have a new quiz in Canvas and we have plenty of time. Let's see, this is, yeah, we have an hour. We have an hour to be in Canvas. Okay, so hop into Canvas, borrow a Chromebook if you want. There's this quiz right here to take. Again, this is your this quiz, the new one, is your 7th grade in Canvas for the unit. Take a moment and click on the grades tab in Canvas and make sure you've got 7 grades, because if you don't, you want to go back and take care of them. I don't see you again until Monday. And we're going to do our last math gas law then. I'll see you then Wednesday. We're going to do lab and start a review. I'll see you Friday. We're going to finish review. And then the following Tuesday is your test. So our unit's coming to a close very quickly, especially with the STAR testing going on next week. Don't let yourself fall behind. Now, today is a great day to do this quiz and catch up on old ones. So please take a moment to look into Canvas at your grades. Let me know if I can help on this quiz or any others. Let's put this time to good use. Go for it. Make it happen. Okay, the question is what's happening Friday? Nothing. It is a complete day off of school. So you all sleep in. I know I'm going to try. I have a crazy 10-year-old who likes to get up like around 5. Like literally, that's his daily goal, to get up after 5. I'm like, no. He likes to watch YouTube before he eats breakfast. And apparently he needs hours. I'm like, Okay, get up and just go away then. But don't try to get me up with you. It's sad. It's wrong. I'm like, you're 10. You can handle it. Here's a box of cereal. Don't wake me. Yeah, I mean, that's it. He likes to, especially he's doing online schooling still. So he likes to play some video games before he has, but he likes hours. I'm like, no, you don't need to get up that early. I don't understand. So Friday, enjoy your day off. Have a restful 3-day weekend. I don't see you again till our next odd day, which is Monday. So do plan to show up here again Monday.